Stefan, Muller, and my friend me, which I'm grateful for. What if we could write a web server that checks for denial of service attacks in the background, scientific simulations which gather new data while computing, and an LLM with continuous training, with fast parallel processing and I/O responsiveness in one elegant language? Let's show how this is not only possible, but more flexible than ever, and prove it by writing that web server. But first, let's see how fast the parallel processing and I/O responsiveness are usually achieved separately. Cooperative multithreading breaks down computation into smaller tasks spread out across multiple processors in parallel. Decades-long research has proven formal efficiency bounds to maximize throughput. Competitive multithreading, on the other hand, hides latency of I/O-bound tasks, time slicing on one or more processors, completing them concurrently. And it's competitive because it uses thread priorities, and the scheduler favors higher priority threads for high I/O responsiveness. Responsive parallelism is the combination of cooperative and competitive multithreading, and it has all of these benefits of both. To prevent a common bug that needs to be prevented for responsive parallelism is priority inversion, where a high priority thread waits for a low priority thread to finish. And PriML is from a recent line of work, a key language for responsive parallelism that prevents priority inversions, and we'll see how. But first, let's see the PriML commands. You can spawn a thread at any priority and sync on a thread. It blocks until the thread returns its value. A PriML thread is simply a sequence of commands. Let's see this priority inversion. We have a high priority thread, which is waiting for TD, a low priority thread, and it's not finished yet because we have many medium priority threads that are taking up all of our processor time. So we have a priority inversion. We want our high priority thread to only depend on work in parallel that's at a higher or competing priority. PriML currently uses its type system to statically rule out priority inversions. We have the sync rule, simplified for clarity. We have that the priority of the thread we sync on upper bounds the priority of our current thread. So PriML threads are safe from priority inversions. PriML combines cooperative and competitive multithreading into responsive parallelism, and it has all the benefits of both. Almost. Right now, PriML is limited and inflexible, and we'll see why. Competitive threading systems usually use integer priorities, and we expect to be able to calculate on them and bind them to variables since they're first class. Here we want to increment the current priority, but priorities are not first class in PriML yet. If we return to our web server, our classification loop runs in the background, classifying clients as malicious. And in the foreground, we have our accept loop, which accepts new clients in the foreground. And we want to be able to handle a denial of service attack by changing our priority of our classification thread to a higher priority so that we can pay attention to malicious hosts until the threat is gone, and then we return to a low priority. But changing priority is not possible in PriML. So we extend PriML to solve these limitations, making priorities first class and adding dynamic priorities so that a thread can change its priority using our new change command. So let's redesign PriML's type system for dynamic and first class priorities, which introduce endless possibilities. There are multiple priorities that the thread runs at, and a priority expression can evaluate to one of many possible priorities only known at runtime. But why are so many possibilities a problem? We might run into priority inversions. And so we need to modify the Cilk rule to rule out priority inversions. Currently, we only have single priorities, and so we can't account for all of the possibilities that we have with dynamic and first-class priorities. To solve this, we use refinement types, which give us all of the constraints that we need. A refinement psi can represent the multiple priorities a thread can run at. Here we have a thread with 3 priorities, and a refinement can represent the possible priority values that an expression becomes at runtime. Here this will be high or low, and its refinement has both of those priorities. A refinement limits a priority possibility using a construction of constraints. For example, if we have a priority P such that 2 is less than or equal to P and P is less than or equal to 5, we have the priorities between 2 and 5, and we use set notation as an abbreviation for clarity. So right now, our Cilk rule has that the priority of the thread we sync on is an upper bound for our current thread's priority, but we want to use refinements to represent all of the different possibilities. So how do we do this? Refinements upper bound the many possibilities of those 2 different possibilities using this refinement judgment where the possible priorities of the thread synced on is an upper bound for the current thread's possible priority value. And this is defined as all of the priorities in the first refinement must be less than or equal to all the priorities in the second. So before we had first-class priorities, priorities had no type, but now we can use a refinement to type all of the possible values it has at runtime and do the same thing with threads, replacing the single priority in the old thread type with all of the possibilities in this refinement that it can run at and change to. We also need to update PriML's command type because, as I said before, a PriML thread is a sequence of commands. But this is not as simple as replacing a single priority with a refinement. I'll show you with this example. We have thread B taking on priorities 10 and 11. We know its type here, it's an int thread. And thread A increments its priority and syncs on B. We have that. The sync command is only allowed to start at priority less than or equal to 10 in order to prevent a priority inversion when syncing on B. And the change command changes the priority so it has 2 priorities in its duration and it ends at a new priority. So we need 3 refinements to type a command: the start, duration, and end refinements. our new command type has these 3 refinements in it, and this is what we need to rewrite our sync rule. Our new sync rule has this new bound premise where we have that the starting priority is, okay, so we have that the priority of the possible priorities of the thread that we sync on is upper bounded by is an upper bound for our start priority of the current thread. And all 3 of these refinements are the same because when we sync, we don't change our priority. So now that we know how to, now that we can show that our threads depend only on higher and competing work in parallel, we can type a thread. Here we have thread C trying to sync on thread D, which takes on priorities 4 and 5. First, it changes its priority to either 3 or 5. And so we get all of the start, duration, and end refinements for each of these commands. And in the interest of time, I won't go through each one of them, but when we sync, we're definitely at one of the priorities 3 or 5, and we have to check with the sync rule if we have a priority inversion to check if the priorities 3 and 5 are upper bounded by D's priorities 4 and 5. But this violates the sync rule, and so we have a priority inversion. So let us fix this bug by adding a change command and change to priority 4. And now when we sync on thread D, we check if the priority 4 is less than or equal to the priorities 4 and 5, and it is, so we have the upper bound that we need, and we can give thread C its type. First, we need to know what priorities thread C takes on in its whole duration. To do that, we take the union of all of the durations of the commands, which is our intuitive strategy. Formally, we use composition and subtyping, but we know that this thread C takes on priorities 1 to 5, because it starts at 1, and it changes to priority 3 or 5. And so we can find the type for this thread, which returns an integer. So it is an int thread with priorities 1 to 5. Now, how do we bound the response time of our threads? Well, we just redesigned PriML's type system, and our program can now become a well-typed program. And we need to prove that this well-typed program gives us our efficient response time. To do this, we have a cost semantics that turns programs into directed acyclic graphs. And we restrict these graphs to be well-formed, which is a key property we prove means the graph has no priority inversions. And we use our cost semantics to turn our well-typed program into a well-formed graph. And we prove that with a well-formed graph, we will be able to bound our response time efficiently. And the entire proof you can see in the paper. Now let's see PriML's new implementation with type inference for dynamic and first-class priorities, which is inspired by liquid types. And we have a new backend which compiles PriML to multi-core OCaml. And finally, we return to our web server again. Here, our web server changes its priority depending on how many connections we have, which is how heavily loaded the system is. It also calls process hosts because the classification needs to know which hosts are bad hosts that may be overloading the system. When we first wrote our program, it had this error. I'm sorry. Am I over time? Okay. Okay. We fixed this bug using dynamic and first-class priorities, and PriML is now flexible and has a proven efficient response time.